This comes to life at some point in time. Okay, so last week I was cruel and unusual and I tormented you guys with mesh control. Right? So what did we do with mesh control?
We made sure that the mesh was finer at the points where we think the stress is going to be the highest.
Excellent, excellent. And how did we do that? We went in there and we kept refining the mesh until we thought, oh, it's great, right? And then we're not going to mess with it anymore. Okay. Adding in nodes. And some of the ways we tell when we have problems is that we look for areas of high stress gradient. We don't like nodes that are the adjacent nodes that are significantly different stress levels, because any error in those calculations can be way off. So we tend to search for things that are smooth or the gradient between them isn't particularly high. And so this is a problem I gave you guys last week. Everybody's done, right? Okay, everybody's done. Well, you're all going to do your mesh control on this, and it's happy. It's easy, right? You have to model what? A bar and a hole and a notch. And then 2 notches. But no, you only have to model 1 and then mirror. Right? Okay. So we're leaving getting it easier here. So so now if I run this, of course I see areas in here that are unhappy, and I can tell if I go do my probe thing here that I've got 1 node in there, right? And the next node, you can kind of see it as it runs down to this edge here and over to here, right? I mean, I have a very high stress gradient. It goes from being 29 to 21, so it changes by about 30%, right? And that's in a node, right? And I'm even worse if I go down here. And there's nowhere in between here I can click because there are no nodes in there, right? The next node's over here. It's 20, at least these two are pretty close to each other. But then if I go down in here a ways, right, I mean, they're dropping off really significant, and there's nothing in here I can click to because there's no nodes, right? So there's a huge stress gradient. I mean, we go from this area here, which has about 3 KSI, and then we're dropping all the way off. Not sure where that one's actually picked from. I didn't see, where is that guy at? Oh, it must be inside there somewhere. Must be inside a node that's inside of it somewhere. So these are all the nodes on the outside, so it must be an internal one in there. I don't think there is one in there. So anyway, okay. So that's always a headache. And last time, as I had you do this, we went and played with mesh controls, right? Okay. Well, and what do we do with mesh controls? We put finer controls on it, and then we do this convergence study, which we did on the board last time. Where what do? You run it and check one result, and then you run it again and check the result. And while we can do this gets to be a bit tedious. Doesn't it get to be a bit tedious? Or has nobody done it, so it hasn't gotten tedious yet? Okay.
Yes.
Okay. I think I answered my question, but it wasn't the tedious part of it, right? Okay. So but yes, it does get a bit tedious. We're playing with this, and of course, all we're really doing is refining the mesh geometry, and then checking to see if it's convergence. And so someone might think about, I wonder if you could automate that.
Can you automate that?
Could you automate that? Funny you asking there, Brian. Okay. Could we automate that? Well, what do you think? Could we automate that?
I'm guessing
Yes.
We think we might be able to automate that. Because I think all we're doing is just changing the mesh density, right? And shoot, it's coming from the geometry. We're not changing the geometry. So maybe we could come up with an algorithm that would go in and automatically add mesh control and just remesh it and rerun the analysis until we got an answer that we were, well, that at least converged, or we ran out of time, depending on what we wanted to do. Okay. And so one might ask is, could you do such a thing? And the answer would be, well, yeah, you can. And actually, as about a year or two ago, SolidWorks actually added that capability in. So I actually have to take advantage of it. So if you wander to, and I just pulled up this model because it's sort of one that we look at here. And if you wander up to the top level here in your analysis, in this particular part of art, you right click, you pop this menu up here, and partway down here is properties. Right? Like 2/3 of the way down, maybe 60% of the way down. You're right clicking on the top item in the simulation tree, and then we get properties down here. Right? And if we click on properties, it pops us a menu. These are all the properties for the static option that SolidWorks gives us. Now, if this was ANSYS or MSC Nastran or Abacus or any of the fancy ones, the number of options that would give us would be so large as to, shall we say, confuse all of us. But in SolidWorks, there's nowhere near so many options, so that but there are some in here, okay? First of all, we have a section in here that's gaps and contacts. This is what do we do if we have contact elements as elements that aren't actually connected but are hitting each other, okay? We'll talk about what we do with those later. I'm not going to talk about them now because they're ugly, but that's okay. We'll talk about, we're going to do those later. And meanwhile, we don't have to worry about it. Incompatible bonding options. It says automatic simplified or more accurate. Who the devil knows what that does? Okay. Well, it's on automatic, seems to work. Leave it alone, don't ask questions. Think that works? Okay. Okay, down here we have large displacement. This is a large displacement flag. Okay. If the problem starts exhibiting large displacements, and sometimes yours may, and in fact, sometime during this class period, you'll get a warning goes up, large displacement. Should I run with the large displacement option? Almost always means you screwed up your boundary conditions. Okay? Not guaranteed, but almost always. But it's not quite so badly failed that it's just given up, catastrophic. By the way, if you turn on the large displacement flag, say let it run, okay, it will run in the large displacement mode, and then when you don't like the answer, the large displacement mode won't go away. Which leaves the question is, what the devil is the large displacement mode? You're almost as quiet as the UWB class.
The non-existent one?
I have a UWB
Oh,
class.
okay.
Okay, there we go. That's a little better. Okay, yes. Okay, so what's the large displacements? What's this large displacement option? Well, if it's not large displacement, it must be small displacement. There we go. I got an answer. Yes. Congratulations, Jazz Deep here. Okay. Okay. It's none of the rest of it. And Sophie's trying to jump in here too. So none of the rest of the people are in the back of the class that are asleep. So that's the okay. So what's this large displacement thing here we got going on? Well, it's opposite small displacements. We usually assume small displacements. And this is an old one from Strength and Materials that you've probably forgotten. What's the small displacement assumption? Well, there's a small displacement assumption in all of your Strength and Materials analysis. It's that when you load the structure does not deform sufficiently for the static loads to change. That is, when it bends, it doesn't bend and shorten enough, or doesn't bend enough for any of the load conditions to change, right? Or the changes in them to be significant. Because if you think about it, if you have a cantilever beam, right, and you're bending on some real complex geometry that you'd never ever do, something like, okay. Okay. What's that doing? Well, we get a stress out of that, right? We get a stress back here, that's, right? What's our stress in the beam?
Shear stress. Shear stress.
F over A.
I've heard the right one.
Bending shear, you're saying, or? You were right.
What's the stress in the beam back here?
F over A.
And what kind of stress is it? That's a normal stress, yes. That we tend to write as a bending stress, right? That's a stress, right? So, we make this out of some nice rectangular cross section, right? We have that gives us our I, that gives us our C, or a circular cross section, right? Doesn't really matter, right? Either case, or even it does some other shape, as long as it's constant, right? The I is constant, as long as it's constant cross section, doesn't really matter. We can make it any shape we want. But guess what? M is a function of
Where the force is applied.
where the force is applied, how far a force applied. Well, if we load it up, what happens to this beam? It bends. Does that change the moment?
Yes.
If your distance changes.
Yes, now the assumption in strength of materials is that it's a small displacement. And so the assumption is basically that it doesn't bend enough for this length to change. Right, that's a small displacement assumption. Things don't bend very much. Okay, when a large displacement is that, oh shit, it did bend a lot, right? It went like this. Right, and now our force is not out over here, now our force is over here. Right, and what did that do?
The moment arm got smaller.
Moment arm gets smaller. Absolutely. Do parts do this? Only in your nightmares? Yeah, they do. This is the large displacement problem. It's how do you solve this? Oh, X deleted. How do you solve it? Well, in order to find the moment arm, what do you have to know? You have to know how much it bent. In order to know how much it bent, you had to know what the stresses were on it. And in order to know the stresses, you had to know the moment. But the moment's a function of the length, so you don't know that because it's changing. So you're going, what are we doing here? Okay. I finally got somebody to chuckle there, okay. So what do we do? What do we do? Well, what the FEA package does is it guesses. It goes, well, okay, what do I think the displacement's going to be? Well, I don't know. So what I'm going to do is I'm going to run it, and I'm going to do displacement. And then what I'm going to do, oh, okay, that moved far enough to move this point here. And then what we do, well, we got to move it now. So we recalculate the statics, and we rerun the analysis again. And see how much it changed. And so now instead of going through these once, what are we doing is we're going through them multiple times, iterating through them until they converge. And it's going to go through it at least twice, always, because otherwise it doesn't know it's converged. And the only way it knows it's converged is it runs it once and then it runs it a second time and the answers doesn't change very much. Right? That's the only way it knows it's done anything. So, shoot, the instant you put a large displacement flag on this, it's going to run the analysis at least twice. And that assumes that it converges. It may run it more than that. So it's going to slow you down, even on some of these faster analyses, quite a bit. Now, oftentimes what happens, and I'll warn you all, oftentimes what happens is you go, ooh, you get that large displacement flag, you go, I'll run it anyway. Give me a picture. Tell me what you're doing wrong, because I don't have a clue. That's what we all do, and then it goes, oh, okay, well, if it survives, which is like 50-50, and I might be optimistic at that, maybe you could look at it and go, oh, yeah, I did screw up that boundary condition. I forgot to do something over there, and so it doesn't make any sense. So you fix it, but it sets that flag, and it runs large displacement every time. So it takes twice or 3 times as long to solve as it should every time. You can pop this window, come back, and just click this off, okay? And it will quit doing that behavior, okay? Just so you know. Now, I don't really care. It's your CPU cycles. I don't have to wait for it to run 3 times. I know where the flag is. Okay, so I've now told you where the flag was.
So where do you find it? Other than looking here, is there another indication that it's doing?
Oh, it'll run twice when you run the analysis. It'll run through it once, and then it'll run through it again. Okay, at least, and sometimes more. I might show you a little later. Okay, so anyway, that's one of those things to do. There's also what's called the solver down here. This is the what kind of matrix solver we're using here, right? Again, we're making this great big matrix up with all of the equations, right, for all of the nodes in there. That's all relationship, and that's a huge system of simultaneous equations, but it's a very sparse matrix. It's almost always on the center diagonal because the nodes are related to each other, and so most of the terms are 0 because most of the nodes aren't connected to each other, right? Most of the only equations are between nodes that are close to each other that are basically connected in the form of an element. And so, since that's a reasonably finite number of them, most of the matrix, since you wind up with this huge matrix that's thousands by thousands, but most of it's zeros, because the nodes aren't connected to each other, there's no mathematical relationship between most of the nodes. It's just the ones that are connected in elements. So there's a bunch of different solvers in here that you can use. The FFE plus, which is the default, is not bad. You can click on the others. There's a sparse solver, and there's large problem direct solver. I haven't found any of them that work any better than this. Sometimes if it refuses to run and is stubborn, you can get it to run with using one of the other solvers. It takes a little bit. I didn't like that one. That's because the mathematical techniques, which is you'll learn in numerical methods, there's a whole raft of mathematical techniques for solving systems of simultaneous equations. And frankly, do I care? Oh yeah, I'm really glad that somebody works those problems, and it's not me, right? I don't want to work those problems, right? I let math people work those problems. And there's a really good market for math people working them, but most of them have been solved, and we have methods that work really, really well, and they're amazingly fast for the huge equation solutions sets that we have. And we just don't care very much, right? Okay, that's good. So anyway, so why did I pop this up over here? Well, if all we had is a large displacement flag and a solver, and if you don't screw up, it's not going to ever do anything with that. Well, that's because up here on the top there are tabs. And one of these tabs over here is adaptive. Okay? And usually I don't teach students this till the end of the quarter. But they grumbled at me when I did that last time, so I thought, well, okay, if you insist, I'll do it a little bit earlier here. So, we have adaptive method, none, H adaptive, and P adaptive, which is okay. What the H is H adaptive, and what the H is P adaptive, and why should I choose one over the other? Well, it winds up that there are 2 different systems for basically solving, well, I should say 2 different methods for doing the convergence studies, okay? The first one was what they refer to as H adaptive, refers to H elements. And H-type elements are the ones that I described. They're just an element. They're nothing fancy about them. They're a relationship between the nodes. And we know from the underlying, somebody, one of those math types went out and proved that for H elements, okay, if you add more nodes and more elements in, that as the number of nodes and elements approaches infinity, the solution approaches, asymptotically approaches the theoretical. Okay? So those are the H elements, standard everyday elements, nothing fancy about them. And so H adaptive, this H adaptive here, is just using the standard elements, standard everyday elements. And the only way it has of doing a convergence solution is to add more elements. So that's what it's going to do. It's going to do exactly the same thing you did with mesh control. It's going to go look at areas with high gradients, and it's going to add extra nodes in there, and it's going to rerun them. Okay, that's exactly what it's going to do, and it's going to work pretty darn well. Now, P adaptive refers to P elements. So, which leads the question about what the blankety blank is a P element. Did I say that out loud? Okay, what's a P element? I don't know. Okay, well, it's not an H element. Hey, it's one of those Microsoft help answers there, right? Okay, so we're working on this. But, okay, well, what the notion was is that, let's say we have an element. I'll have some sort of triangle here, right? And we say if it's an H element, we can go through and say, well, we're going to have a spring in here, and we can model this as springs, right? Okay. Now, if we really wanted to get carried away, right, we could say that, hey, well, you know, we may have a triangle here, but we're really going to be a little smarter about this. So we can actually make an element that is a subset of triangles. Okay. So we've got our nodes out here on the ends, but we're actually going to calculate some intermediate ones. And we'll have some springs here, and we'll have some springs here, we'll have some springs here, but we'll also get springs in here, and springs in here, and springs in here. And of course, these are not only I'm just drawing the linear springs, but there's actually torsional springs as well. So we get all of these things there. Now, what this is doing, this is one of the ways we can make up an element that actually has more intermediate points to it. Okay, and people do this. What these do is these get mathematically more complex. Now, I can do that by adding additional points into there. Also, I can do this by saying, hey, you know, this is a spring. Maybe I can think about this as springs. Okay. But do the springs have to be linear? No. You know, we have a what? F is equal to kx, right? And that assumes that the spring is linear. Now, does it have to be a linear spring?
No.
Can I make a higher order spring that has second order and third order and fourth order and fifth order? So instead of being a nice linear equation, now it's going to turn into some sort of nasty polynomial thing and get worse and worse and worse and worse. And yes, we can. Okay? And that's what a P element does. Okay? These are what are known as shape functions. Okay? They're usually more complex than linear. They're what's known as a shape function, and I can get nasty ones. I can raise the order, so instead of being linear, it can be quadratic, right? Because it's got a squared turn, or it can be cubic, or it can be quartic, or quintic, right? And I can raise the order of these out, add higher order terms. Now, the P element people, there were a lot of people that bragged about P elements a lot, because one of the things you can do with them is you can represent things that are curved to begin with. like if you have a curved, elements around the curved hole, you can represent that curved hole as a second order element, as a second order shape function, and get the curve, because you've got it in the geometric representation of it. It's already curved, right? Its shape is already curved, and that's so there were people that built FEA solvers on P elements. And one of the advantage to P elements is it was real easy to add the higher order terms. And so when you wanted to do some sort of automatic convergence, what you just did is said, well, I got a shape function here. Your shape, I'll just increase the complexity of elements where we need it. And well, does that work? Now I've got UWB quiet again. Okay. Well, it seems to. There is no proof that anybody has been able to come up with that increasing the order of the elements, that is increasing the complexity of the shape functions, actually converges to the same solution as the theory does. There's no mathematics that prove that. Yet, for every case that people have been able to come up with, it seems to. That is, there aren't any cases that are valid. I mean, you can always get one that blows up for a stress concentration or something, but then everybody blows up, so it doesn't really help it that, you blow up when everybody else blows up. It doesn't, that's not necessarily helpful. So P elements are what we're gonna do is we're not going to actually add more elements. We're going to just refine the ones that increase the order of the ones that are there. Now, since we have both of them, and who knows really what they do, let's go play with them. Okay, so I'm going to go click on the H adaptive here, and of course I get all these parameters up at I get the target accuracy, I get a accuracy bias, and a maximum number of loops, and am I going to let the mesh coarsen, which is that am I going to let it, the mesh get less dense in areas where I don't need it. And since I'm playing with it, just see what happens, let's go take a look at it. Right? So what I'm going to do here is I'm going to, of course, I crank the accuracy up as high as it'll go, 99%. I crank the bias up as high as it'll go. Accuracy bias, if slower, I assume is better, but who knows. Maximum number of loops, I think yours is 4. I go as high as it goes, because if you're typing something bigger than 5, like 7, what's it going to do?
Go back to 5.
It's going to go say you got between 2 and 5. Okay. Right? Okay. You don't get any choices there, right? And I'm going to put the mesh coarsening on here. Okay? So if we look at the mesh for this part, and I'll show you the mesh for this part to start with. We show the mesh. This is what the default mesher gave me, right? Gave me sort of one element thick, right? Kind of going around here. And if I run the guy, it's going to run multiple times, and you can watch it refine the areas in there. So here's the 4th time through, and now it gave up after 4 times, right?
This
gave
is
up
the,
after 4 times.
the H.
This is the H adaptive. And if I look at the mesh, now, I'm going to show the mesh. This is my new mesh. You can see what it did, right? It started out with it all sort of coarse and general, right? All uniform, spread out, right? That's what it started with. And what do we have? We got a whole bunch of stuff right over here. We got a whole bunch of stuff right in here. And I've even got some stuff going on down here. I may not care about what's going on down here, but I do have weirdness going on down there from my boundary conditions, right? I get strangeness from the gradient, from the boundary conditions. Well, that was pretty nice, wasn't it? Guess what? When you run this, it always starts with the mesh that you have to start with. So while it only goes through the loops 5 times, if you're not happy with that, just
Increase.
run it again. And then what it'll do, it'll try to loop through it again, because it doesn't know if it's converged. Right? Okay. So I can look at this current mesh here, for example, if I want to do some sort of details on the mesh, looks like I have, 26,000 nodes here. If I just run this again, hold on. It gave up on me, didn't run it another time because it was happy with its convergence. So it's not gonna be different, darn it. Gonna have to beat you up, so. Actually, it did, it increased the density of the nodes by a factor of 2. So it must have ran twice. So if I look at the mesh now as a new mesh, let's show the mesh, right? It got even finer over here. Right? And you can keep rerunning it. Every time you rerun it, it's going to get a little finer because it has to go through at least one loop, right? So it'll have to go through at least 2 loops typically because it has to check and see if it changed from the prior loop, right? So, okay, that's H-adaptive. Actually works really well, and I'm a big fan of H-adaptive, okay? Works really well, crank it up, gives you lots of nodes and accuracy where you need it. Doesn't give you a big mess where you don't need it, right? So, and you can see over here on the end, what happened, the elements even got bigger. Right, they were smaller originally, now they got bigger, that's because I had that mesh coarsening flag on. It got bigger over there. Not that I cared, but what does it do? Because it didn't need it. Everything's uniform over on that end, which is what we expect for a force pulling on it. Isn't that nice? Okay, can I get back to the beginning? Well, yeah, what do I have to do? If I try to change this to p-adaptive now, what's it going to do is it's going to try to p-adaptive on this mesh, which is, well, it could do that, but it's kind of not necessarily a real great idea. So what I have to do is I actually have to go create the mesh, back to the beginning, throw away all the results, start over here. I have as coarse as it goes, and there's the original mesh I started with. Right, my original mesh here I started with. Let's go try the p-adaptive. Get the properties up here, we'll go adaptive, we'll try the p-adaptive, and might as well stop when the total strain energy is, let's go, 0.5, how about 0.25, just try to squeeze it down there. And the relative strain generator is less than 0.5%, and we'll start with the second order, and the maximum p order goes to 5, and it's only gonna go through 4 loops, and those won't go any bigger because, well, the first one will, but there's no real reason to do that. That's just making the whole thing more complex. So I've got the P order and the maximum number of loops pushed about as far as they'll go. And I can run this now, and it'll sit here and chug, loop 2, loop 3, and there it goes, quit after loop 3. And you see it never quite got the refinement. When we zoom in here, it never really refined the